Thank you for the introduction and thanks for having me second time. Last year we did a talk together with Andre about benchmarking. This year I will focus on profiling. I'm one of the BenchmarkDotNet maintainers. I currently work at Microsoft on the .NET team, where I'm responsible for building the performance culture. I profile a lot, I benchmark a lot, and I have some experience that I would like to share with you, so you can use it as well. When it comes to performance, the first rule is that there is no place for guessing. We should be always measuring using the right tools. No matter how experienced software engineer you are, you shouldn't be trying to guess. Because without data, you are just another person with an opinion. And which tools should we use? So a benchmark can tell us how long does it take to run given code, while a profiler can answer a question why it takes so long, and what exactly took how long. And profilers are the most important part of every software performance investigation. And how do we get started? First of all, we need to start with the recommended settings. So we should be always measuring the performance of release builds, never the debug builds. The debug builds have 0 optimizations applied. One important thing, to help the profilers to solve symbols better, you should enable debug symbols, which basically contain information and help profiler to connect the CPU samples with the source code. And third very important thing, recently we have shipped .NET Core 3.0 and it has TierJIT enabled by default. And TierJIT has some warm-up heuristic. And if you have a small repro case and you are not profiling startup time and you don't know how to properly warm up your code, then you should just disable the TierJIT, because it's going to make your investigation and analysis simpler. The next step is to prepare the small repro case and to try to narrow down the problem. As an example, I'm going to talk about a thing I was profiling a while ago. So as you know, .NET Core 3.0 introduces new APIs for vectors, so-called intrinsic APIs. And basically, we have implemented a managed library that uses them, and we have a target framework to ML.NET. The new version, which was using .NET Core 3.0 and managed API, was slower than the .NET standard implementation, which was calling a native math library. So to narrow down the problem, I have disabled the TierJIT and run the benchmarks for 3.0. By doing that, I was able to make sure that TierJIT is not guilty here. Second of all, I have updated the version of .NET Core runtime to 3.0 for the version with native dependency. And by doing that, I was able to narrow down the problem that it's not .NET Core 3.0. So I was able to say that, hey, the problem is in the vector math library. And this is when we start the profiling. This is my list of personal recommendations. So when you are on Windows and you are developing with Visual Studio, and you can reproduce the problem locally, you should start with Visual Studio Profiler. Otherwise, if you are still on Windows, you should give a try to Paraview. On every OS, you can give a try to Dotnet Trace, which is the new shiny thing which I'm going to demo soon. And if you're on Linux and you care about native call stacks, you should be using PerfCollect. So now I'm going to switch to the demo. OK. I have disabled the internet, and Visual Studio is offering me an update. How cool is that? So the app is doing something. It doesn't really matter what the app is doing, but the most important thing that I'm in the release mode. I'm having the recommended settings in place. And now I need to profile the app. So Visual Studio Profiler is hidden in the debug menu item under the performance profiler. When I click it, it offers me a few options. So by default, you should be starting with CPU usage because you haven't profiled it yet, and you don't know if it's a problem with memory or I/O or database. So our default choice should be always CPU usage. And now we just start the profiling. It's very important for your repro app to run for at least a few seconds so the profiler can gather enough data to show you some meaningful results. And now we are done. We can see that it was running for something around 5 seconds. And we can see the first screen. So first, two very important things: total CPU time and self-CPU time. Or maybe, as other profilers call it, inclusive CPU time and exclusive CPU time. So inclusive CPU time is whenever given method is on a call stack. So it was executed somewhere. For example, a main method should be always close to 100, while the exclusive time is when the method was the last thing on the call stack. So this is when it was actually doing CPU computations. And in performance investigation, we are looking for top exclusive time contributors because they're doing the most work, and this is what we care about. So first, very trivial thing, we can just sort by exclusive time. And as you can see, I already know where we are spending 36% of time. However, you can also go in other direction, and you can just dig in from main and move forward. And as you can see over here, Visual Studio is telling me that source information is not available. So recently, Visual Studio Profiler team has changed the moment when the symbols are loaded. Now it's on demand. So I actually need to right-click on the method and say, load all symbols. Now I'm getting back to my report, and I'm clicking in main. And as you can see over here, I have CPU time per C# code line. This is the biggest advantage of using Visual Studio Profiler because it's highly integrated with Visual Studio. So it gives you really great overview of what is happening. Another thing you can do over here, you can just click on the expand hot path, and Visual Studio is expanding the call tree to the place where most of the CPU time was spent. Let me get back to color collie view. As you can see over here, we have more kind of visual representation. We can just click, and here we can see that something around 50% of time is spent in get natural color method, another 50 in get reflection color. So this is how I just found two performance bottlenecks. As you can see, it's not hard. You are just few clicks away from it. And again, you should really not be guessing. You should be using the profiler. And the other option that we have, .NET Object Allocation Tracking, when during the CPU investigation, it turns out that .NET is spending few percent or more of the time doing garbage collection, you should analyze the allocations. And Visual Studio also allows for that. The time for this demo is limited. I'm going to demo 4 other profilers, so I will just show you the screens. Basically, you get the information of which types were allocated in which method, and Visual Studio Profiler supports both native memory allocations and managed memory allocations. And you can also go from the profiler to the source file. The other profiler that I have to talk about, because it's the most powerful .NET profiler, is Paraview. So I would call it the ultimate .NET profiler. It's actively developed and maintained. Moreover, .NET Runtime team is contributing to Paraview. So Paraview is always up to date with latest .NET Runtime features with things like TierJIT and whatever next coming to .NET Runtime. What is very important for you, it's production ready. So it's digitally signed by Microsoft. Moreover, when you're using the default settings, it has a very small overhead, something from 3 to 5%. And it's been battle tested at Microsoft. We are using it to profile things like Bing, Azure services, like dozens of people use Paraview daily. And one important information, Paraview is open source. So whenever there is something that you are not particularly happy about in Paraview, you can always help us to improve it. The first important information over here, when I just start Paraview, it offers me link to tutorials and tutorial videos. Vance Morrison, the .NET Performance Architect, has recorded few great videos about using Paraview. They are all available for you on online.com. So if you ever struggle with Paraview UI, which isn't simple to use, by the way, you should watch these videos and then get back to using Paraview. But I would say that using Paraview is really simple, so I will just now try to explain it to you. Paraview offers us two options. We can either run an executable or a command, and then Paraview is profiling the startup time, the execution time, and the rundown time. Or we can use the collect option, which requires us to manually tell where to start and stop profiling. So when you are dealing with issues in production, you are typically collecting. If you have a small repro case on your local dev machine, you are typically running. So now I will go with run. The thing I need to provide is path to executable, which is the demo that we have been just running. Over here, I'm telling Paraview, please don't zip the trace file. I'm not copying it anywhere. I just am going to mention that over here we have advanced options. In 95% of the cases, you won't need them, and they're explained in the videos. And now I will simply run the command. And now Paraview is profiling for me. And here, very important information, log. Whenever Paraview doesn't work as expected, you can just go to log and see what is exactly happening. And this is the place where you might find answers for some troubleshooting. But typically, Paraview works really great, so I hardly ever need to use the log window. And now it has finished the profiling, and I'm opening the most important information, CPU stacks. And here, Paraview provides me the list of all of the processes. The thing that I haven't mentioned is that Paraview is internally using event tracing for Windows, which allows us to capture the data machine-wide. So we can profile all of the processes which are running on given Windows machine at the same time. It's awesome when you're having a lot of microservices that talk to each other, or you are trying to profile Visual Studio, which is spawning a lot of child processes. And here Paraview tells me, this is the list of processes. I have sorted them by CPU time descending. So the top busy processes are at the top, and our process was the most busy one. So I'm just pressing OK. And the first thing that you need to do is to take a look at these two numbers, total metrics. So Paraview is a sampling profiler. It means that at configure time interval, which by default is 1 millisecond, it takes a snapshots of all of the active threads. So you can think of Paraview and samples like of an animation and frames. So it's basically taking picture, taking every millisecond, and then it's aggregating all the data together. The very important thing is to gather at least a few thousands of samples to have enough data to provide some meaningful answers. So yes, we have something close to 4,000, it's fine. Second very important number, metric/interval. This value tells us how CPU bound was given process. And if you are using 100% of a single core, the value is 1. So if you are profiling a single threaded application and the value is 1, then it's awesome because you have used 100% of CPU. However, if this value isn't close to something like half or 0.7, you are most probably dealing with I/O problem. And I/O profiling requires a blocked time analysis, which is another very complex thing. But Vance has recorded a free video, so you can watch it later. I'm not going to cover this topic right now. So we have made sure that we have enough data. It's CPU bound, so we are doing CPU investigation. As you can see over here, Paraview is saying something like other coreclr, other coreclr. By default, Paraview is grouping the methods by modules. It's very useful when you are profiling in production and your app is using, for example, ASP.NET Core, Entity Framework, SignalR, Autofac, Serilog, a lot of different things. So instead of displaying a long list of methods, it groups them by modules. However, I personally like to have a full detailed view, and the first thing that I typically do, I just disable the grouping. Over here, we can see something with an exclamation mark and a question mark. This is something that has unsolved symbols. And I've been practicing this demo before, so most of the methods. However, if you are going to do this for the first time on your, you are going to see this a lot. So the second thing that you need to do, you just press Ctrl-A to select everything and right-click and say lookup symbols. And Paraview is really excellent at solving symbols. So, for example, you can profile on Linux using PerfCollect, copy the trace file to Windows, open it with Paraview, and Paraview is going to solve the symbols for native libraries used in your Linux application. So this is when Paraview is really shining. The second thing that we need to do is we need to filter to set the time range. As you can see over here, we have relative values when given profiling started and stopped. And as I said, we were running an app, so Paraview has profiled the .NET startup time, the JIT time, the execution time, and the rundown time. So I'm this time not interested in anything than the method that I wanted to profile. So I can just go to call tree, and the method was called render. So I just put render here, press enter. I'm just clicking and set time range. So this is basically the 3 steps that I always do whenever I'm using Paraview and I'm filtering stuff. And now let's talk about the data you see over here. As you can see, Paraview, the default tab is by name. This tab shows us the list of all methods sorted descending by exclusive CPU time. So to tell the long story short, the top time contributors are over here. And now, very often when we are dealing with really huge performance bottlenecks, which are very easy to diagnose, they are visible right here. So very often my performance investigation stops at this moment. Some time ago, I've been removing some logs from coreclr. All of them were always at the top. However, Paraview offers us few more tabs. For example, we can right-click on given method, and we can go to callers, and we can see which methods were calling this particular method. We can also call tree and caller and callee view. But the thing that I want to chat about are flame graphs. So flame graphs are the not in text form way of visualizing performance data. And how do we read a flame graph? So first of all, flame graph represents the data which was aggregated all together. And every box width is equals to the CPU inclusive time. And we read it from the bottom to the top. And when I was working on the first version of this presentation for the .NET team, I realized that lack of zoom support kind of sucked. So I simply implemented that. So if you have ever used flame graphs in Paraview and you were missing zoom, it's now there. As you can see, over here we have main. Here we have some coreclr methods, some Windows methods. And basically with flame graphs, what you do, you are basically looking for the big boxes because they are your perf bottlenecks. A very cool thing that Paraview allows us is folding. Requires a value, an integer, and it basically means something like, I'm going to take this value, and for every leaf node, if the CPU inclusive time is less than given value, I'm going to fold it into its parent. So if I'm going to set it, we can see more details. However, if I set it to 5, we can see that the small boxes are gone. They got merged into the parents. And when I set it to 10, we filter more. So if you have a complex flame graph, get rid of all the details and just search for the big boxes, you just need to go with folding. Back to my presentation and make sure that I haven't missed anything. One very important thing, as you could see, I was using method to set the time range. However, as you know, .NET Runtime is capable of inlining the methods. So if you ever cannot find your method in the call tree, it means that either it wasn't executed during the profiling, maybe it was executed for too short and the sampling profiler didn't capture it, or it got inlined. So to prevent this from happening, you can just apply the no inlining attribute to the method. Another important thing, when it comes to reading the flame graph, as I said, the box width is CPU inclusive time. But for all leaf nodes, it's also equal to exclusive time. And when we know that, we can find out that the difference between the child box is the parent exclusive time. Yep. And sometimes it's really hard to filter by method name, because maybe given method was called many times, or it wasn't called at all, or there is something that is simply more than one method, and we kind of want to have explicit stop. So Paraview allows us not to only profile the app, but also listen for events. And in .NET, to emit your own events, you need to derive from event source class and call the base class methods. Like here, I'm calling write event, and I have created two methods, demo start and demo stop. And then in the source code, I'm doing something like this. So at the code where I really want to start the profiling, I'm saying demo start, and when I want it to end, I'm saying demo stop. And now I'm going to show you how to use this cool feature in a more complex scenario. Where are my traces? Okay. So some time ago, working on releasing .NET Core 3.0, and my job was to make sure that we are not regressing the performance. And obviously, we have used BenchmarkDotNet, and we have found few performance regressions. And then we started profiling using BenchmarkDotNet extension called ETW profiler. And what this particular thing does, it emits this kind of event, start and stop. So to compare apples to apples, I'm searching for start and stop events in the first trace file from one benchmark iteration. I'm filtering it. Then I'm choosing the process and saying include item. Now again, the grouping is disabled. I select everything. I load the symbols. They got immediately loaded. Awesome. And I opened second trace file because I want to find out why there is a regression. So I need to compare them. I look for the events again. Here they are. In Paraview, everything works when you press enter. So excuse me, call tree, include item. And again, I select everything, I load the symbols. So on the right, we have flame graph for .NET Core 3.0. On the left, we have flame graph for .NET Core 2.2. And as you can see now, finding where the regression isn't trivial. Maybe some of you have already noticed which box got bigger. The good news is that Paraview has a built-in feature that allows us to compare two trace files, and it's going to tell us where the regression is. So I'm just going to regression, and this magic many item shows up when you have more than one trace file opened. This is very crucial. And now it opened the overview report for me, and we can see that It used to take 250 milliseconds to perform these computations. Now it's 306. But the most important thing that over here, again, it gives me a list of potential regressions. And as we can see, coreclr thread stackwalk frames X was called for 5 milliseconds previously. Now it's for 67 milliseconds was being active during the profiling. So it's basically our regression, and I can just right-click on it. It have opened the colors tab, and I can expand it pressing tab or space, sorry. And over here I can see that this method was called by start the serialization method. And now I could just go to coreclr repo and find out that there was a PR which I have added thing called serialization guard before we have shipped 3.0, and it was done for security purposes. So it's a regression by design. Yeah, but the most important I want you to take from it is that when you have a new and old version of your app and you can see a regression, you just need to profile it, like perform exactly the same thing, profile them, apply the same filters, and then use Paraview to tell you where the regression is. Because as you could see, the alternative is to eyeball all the data. Personally, I don't like eyeballing a lot of data. And by the way, whenever you are doing performance investigation, it's very easy to kind of use the right profilers, but to analyze this it's something hard. And please don't ever feel guilty that you cannot find the performance problem in 5 or 10 minutes. I personally sometimes run into problems when I look into trace files and flame graphs for a week or two. And then I'm able to say, like, we need to change this, this, and that, and the perf problem will be gone. Another cool thing, Dotnet Trace. Dotnet Trace is a new shiny thing. It's a .NET global tool, which means that we can install it with .NET CLI, and it profile .NET Core 3.0 apps on every operating system without running as admin or sudo. It's not using ETW, it's not using LTTNG, it's using a thing called event pipe, which is basically a cross-platform ETW implemented inside the .NET runtime. We did that in order to have the same experience on every OS. However, the disadvantage is that it lacks of native call stacks. However, in most of the times, you will typically want information. So how do we install it? We'll install --global.NET Trace. And that's it. And we are ready to go. So now I'm going to modify my sample app, because .NET Trace allows you to attach to an already running process. It doesn't have the possibility to run an executable. So I need to change my app and basically replace the for loop with while true. While true. And now I start without debugging. Okay, so the app has started running, and now I will use .NET Trace. So first thing, --help. .NET global tool, and you don't know which commands to use. Each of them implements the --help. So the first thing that we need to do is to get the process. So I'm just saying, please. Okay, the process that I'm interested in is my profiler demo. So the next thing that I do, I just say .NET Trace collect -p 4896. And we are profiling. And it works the same way on every OS, which is Mac OS, Linux distro, or Windows. Again, we don't need to run as administrator, which is great. And after we capture the data for a few seconds, I will just hit enter to tell it to stop. And the trace has completed. It has created a new file for me, trace.net trace. Net trace is a new file format for .NET Trace files, but you don't really need to worry about this. The first good thing is that you can actually open such trace file with Visual Studio and get all of the benefits of Visual Studio Profiler. And this is available. Like, you really need to update Visual Studio 2019 to the latest version to be able to use it. Maybe I put it this way. Okay, and as you can see, we have the same information, everything per source code line. The alternative is to open it with Paraview. Yeah. But we all know that not all of our customers are going to use .NET Core and have Windows licenses. Some people are just going Linux way, and this is perfectly fine. And we have tackled this problem by going through the open source and adopting some of the existing open source tools. So actually, .NET Trace allows us to convert the trace files from one format to another. So I'm now going to convert it from nettrace file to format called speedscope. Okay. And what is speedscope? Speedscope is a modern web app that is single-page application. It has a standalone offline mode. As you can see, I'm currently disconnected from the internet. Speedscope is not sending your data anywhere. The license is MIT, and when I go to desktop, yeah, I have downloaded a standalone version of Speedscope. It's basically a viewer for perf data, and now I'm just going with browse, and I'm going to open the Speedscope JSON file. So let's start with the simple things. Sandwich view. Sandwich view is more or less by name view from Paraview. So again, it shows us all the top CPU time contributors. One really cool thing about it is that when you select any of the methods, it shows you the colors and callies. So basically, the tool is very, very intuitive. The left heavy view is, I would call it an upside down flame graph. So basically, it's a reversed flame graph. And again, the data is aggregated. But the biggest advantage of Speedscope is the time order view. This view is very unique because it doesn't aggregate the data. It shows us every profile sample as a separate thing on the call stack. So we can actually use it to find out what exactly was being executed and when. And we can just, hover over the mouse, select something. And personally, I like this feature so much that I even sometimes use it for debugging when I want to find out what exactly was happening in my app. Because attaching debugger on Linux very quickly isn't trivial, so I can just use .NET Trace, capture the profile, and open the file with Speedscope. One important information, because the data is aggregated and it's shown over the time, and we have a single graph, and we have only 2 dimensions, Speedscope is showing you a view per every thread. So there is no possibility to combine the data for all of the threads on a single chart. So over here, you can see that I have only a single thread, so there is no possibility to change the threads, but if you would be profiling a production app, which would be having a lot of threads, then you would most probably see many of them over here. By the way, whenever you're using .NET Trace, you can tell it immediately to export to Speedscope without the extra convert step. But one thing about .NET Trace, as I said, it allows us to attach to a process which is already running. It can capture data for a single process at the same time. and it doesn't have information about native call stacks. We typically don't need this information. However, if you ever get to the point that you need to do a machine-wide analysis on Linux, or you really care about native call stacks, or you want to profile the startup time, then you should use PerfCollect. PerfCollect is just a script located at aks/ms/perfcollect. It has an excellent docs which describe everything. Basically, it's using perf, LTTNG to combine all the data together and to allow for fully featured profiling on Linux. It also knows how to install its dependencies. However, when we end up using PerfCollect, it's producing a trace file which as of today can be opened only with Paraview. We are working on adding support to more viewers. However, as of today, you need the Windows to be able to analyze the data. So how do we install it? We just download the script, make an executable, and run it as sudo with install command. And it's downloading and installing all the dependencies. And the usage is very simple. So basically, we have an explicit start and stop. I'm sorry for the quality. I was hoping that it's going to be more visible. So we start PerfCollect with collect. Then we start our process. And whenever we are done, we just press Ctrl-C in PerfCollect terminal. And it's producing a trace file, which again, we copy to Windows and open with Paraview and apply all the filtering that I have mentioned a few slides ago. And now, we have used the right profiler, we have found some bottlenecks, and what do we do when we find a performance bottleneck? So unfortunately, a lot of software engineers immediately jump with micro-optimizations ideas. But I really encourage you to try to get the big picture and ask, why are you doing these things? So for example, why are we calling this most expensive methods? Maybe we can call it less frequently. Maybe we could cache the result. Maybe there is a newer version of NuGet library that we can just update and the problem will be gone. And architectural changes require more effort, but they can bring you the biggest perf benefits. And when you finally end up, when you know what the code is doing and why, then you can start, applying all the optimizations. But once you have the idea of what you would like to change in the source code, what is the next step? And just a hint, most software engineers forget about this. But during the interviews, everybody claims to do it. The next step is to prepare unit tests. So before we change any code, we need to make sure that we have good test coverage, because we live in a world where correctness is much more important than performance. So first of all, we need to have the tests, and then we can start editing the code. And one very important thing, whenever you are sending a pull request, ask your teammates for detailed code review and try to explain all your design decisions. First of all, you will start building the performance culture, and people will they will start learning all your perf tricks, and in a short time you will see that they also get this performance mindset, and whenever you will be reviewing their code, you will be seeing new tricks that they have come up with. And please don't push on the reviewers, because the reviewers take the responsibility for merging your code and maintaining it. So give them some time, because very often performance changes are high risk, and typically we end up into a situation that we really need to convince the maintainers to actually take the changes. And just to show you how important it is, so a few weeks ago, Kevin has reported a problem that starts with works very slow on Linux with .NET Core. And at this moment of time, I had close to zero information about how complex Unicode really is. So my first idea was like, okay, instead of calling so expensive native API for starts with, I will just subslice the string to the length equal to the length of the prefix and just call string compare, which I know is very fast. And Kevin has very quickly pointed me that there are some languages like French where you can express a single letter with 2 characters. So first of all, we cannot take the length optimization path. And then I started to work on these tasks. And I have learned that this is only one of the edge cases. For example, in Hungarian, we have DZ, which is a single letter. So it doesn't start with D. For those of you who are Polish, we have CZ, which is pronounced as ch. And it also doesn't start with C. However, Windows believes that it does, and Linux believes the opposite. Moreover, we have combining characters, which change the meaning of the previous character. So for example, O with this awesome character doesn't start with O. Moreover, we have null character, which is treated differently on every OS. On Linux, by default, it means the end of the string. We have Unicode surrogates, which are also handled differently by both OSs. And by the way, when I was working on this, and I couldn't convince the code reviewers to merge my changes, which were risky, they started to come up with a lot of test cases. They were basically just try this, try this, try this. And one of them actually wrote a console app that tried to generate a lot of strings and call my method. And it turned out that there was a bug, an 18-year-old bug in ICU, which is a native library used by Chromium and other big projects, where we had unsigned integer 16 overflow. And if you would call B starts with new string A repeated this many times, the answer would be true, because unsigned integer overflow. So as you could see, I was like, OK, starts with is slow. I'm going to work on this before lunch, and I will be done. Now, it took me something like a week to understand how all of this works, and then another week to convince people. So, and only unit tests and code reviewers have helped me to avoid getting into trouble with correctness. And now we have an idea, good tests, and what is the next step? We write the benchmarks. Benchmark help us to validate that our improvements have actually helped. They verify it. Moreover, you should keep the benchmarks in your source code repository to measure the performance over time. So to, for example, make sure that nobody is removing your optimizations in the future. And when we have all of that, then we repeat the iterative process. So we apply the optimizations, we run the tests. As long as they're green, we run the benchmarks. We validate if our optimization improved or not the perf. And then again, we are using profiler, analyzing the data, and repeating the problem, the process, as long as we are not happy about the results. And now a short summary of my talk. Please prepare a small repro, try to narrow down the problem. It's going to make your profiling easier. Always run everything in release when you are dealing with performance issues. On Windows, if you can reproduce the problem locally, I recommend you to use Visual Studio Profiler, which is very easy to use. Otherwise, you can use the ultimate .NET Profiler Paraview. If you ever get into the situation that you don't understand how it works, watch the free videos from Channel 9. On Linux or Mac, the .NET Trace should be your default choice. It's very simple, it just works. However, if you get to the point that you need native call stacks or machine-wide profiling, please give a try to PerfCollect. Analyze the data, don't give up after 1 hour, 2 hours, after a few days. It may take longer. Remember that correctness is more important than performance. Don't sacrifice correctness for performance, never. And use benchmarks to validate the gains. You should never be getting into the situation that you have a benchmark, you change a random part of your code, and you run the benchmark again, hoping that it's going to help. No, you should be using the profiler to identify the performance bottlenecks and solve the actual problems, not guessing. And now we have 2 minutes for questions.
And no, unfortunately, we don't have 2 minutes for questions. So thank you very much. Big applause for Adam Sitnik.
Thank you.